And now for some vector proofs. A, B and CD are diameters of a circle with centre O. Prove that ACBD is a rectangle. Okay, well I found it useful to redraw our diagram here with some vectors drawn in, notably A and C. And we notice that if we've got a vector C, we can have, which is a radius from O to C, we can have a negative C vector, which is from O to D. Okay, so we start off by observing that A plus AC equals vector C. So somehow that tilde ended up on top. Anyway, therefore AC is equal to, just subtracting vector A from both sides, C minus A. And we can also observe that A plus AD, so A plus AD going this way, is equal to vector negative C. And so that means AD is equal to negative C minus vector A. So consider the dot product of AC and AD. I've got the results on the right hand side here. Hopefully you can follow the working. Remember the important identity that the dot product of two vectors that are the same vectors is equal to the magnitude of that vector. So that's how we get down to this line here. And it follows then, because A and C are both radii, that our dot product's going to equal 0. So we've proved really that AD is perpendicular to AC. I think what you should probably do is verify that that is, or just practice that, more than verify, that that is true for DB and CB, and then you'll have proved that ACBD is indeed a rectangle. Take a minute or so to read this one and press resume, or have a go at it, and if you get stuck or otherwise need to see the solution, press resume. So this tricky one, let's have a look at it. The first observation, I've put in a couple lines here, R and symbols, R for radius, and the yellow lines we are going to need. So the first thing I would say is that AP can be expressed as a vector, and when it is, it's equal to AO plus OP. Now we're going to find it more useful to think of that as AP equaling OP minus, we're going to reverse this vector here and call it OA. So we can do that, that's fine. So we're going to find the dot product of AP, and that's going to enable us to say that the magnitude of OP is minus 2OP OA plus the magnitude of OA squared is equal to what you see in this line here, which leads to 3R squared minus 2OP OA. You might want to pause the video and think about that. Now, part B. Well, we can do that by observing that really all we're doing in part B is replacing points on the square points that replace the point A. So what applies to AP applies to BP, applies to CP and DP. So by using that similar logic, we arrive at this set of properties down on the bottom line. Make sure you understand that before we move on. Now this bit's a little difficult to understand, but just bear with me. We can certainly write out this line here based exactly on what we saw on the previous screen. And what I've chosen to do down here is just replace these vectors here with A and B notation so it becomes clearer. So that OA I'm just calling A, and OB I'm calling, would you believe, B, and OC can be regarded as negative A and OD is negative B. In that way, factorising in one thing or another, I get 12R squared minus 2OP, and then this sum here, which equals 0, allows me to conclude that AP squared plus BP squared plus CP squared plus DP squared is equal to 12R squared. Thank you, that is all.